We have learnt that rational numbers are those that can be written in the form p over q, where p and q are integers and q is not zero. We have also learnt that numbers that cannot be written in the form p over q are called irrational numbers. In addition, we know that the decimal expansion of rational numbers can be either terminating or non-terminating repeating. And the decimal expansion of irrational numbers is non-terminating, non-repeating. Without actually dividing, can you decide whether the decimal expansion of a rational number is terminating or non-terminating repeating? Let's learn how we can do this. We have learned the fundamental theorem of arithmetic, which states that every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Let's also see an interesting theorem which proves that the square root of a prime number is irrational. Let's first see some interesting facts on decimal expansion of rational numbers. The decimal expansion of a rational number can be either terminating or non-terminating, non-repeating. Let's consider a few terminating decimal expansions. As you can see, all these decimal expansions can be expressed as rational numbers whose denominators are powers of 10. Let's factorize and simplify these rational numbers so that the numerator and the denominator become coprime. What can you conclude from this pattern? We can say that a terminating decimal number can be expressed as a rational number whose denominator has only powers of 2 or powers of 5 or both. Let's write this formally as a theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p over q, where p and q are coprime, and the prime factorization of q is of the form 2 to the power n times 5 to the power of m, where n and m are non-negative integers. Do you think that the converse of this theorem is also true? Yes. The converse of this theorem is also true. That is, if the denominator of a rational number is of the form 2 to the power n times 5 to the power m, then the rational number has a decimal expansion that terminates. Let's write this converse formally as a theorem. Let x equals p over q be a rational number such that the prime factorization of q is of the form 2 power n times 5 power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. What happens if q is not of the form 2 power n times 5 power m, where n and m are non-negative integers? To know this, let's consider two rational numbers where the denominators are not of the form 2 power n times 5 power m. As you can see, the decimal expansion of these rational numbers is non-terminating, repeating. Can you now write this result formally as a theorem? Yes, we can write the result formally as let x equals p over q be a rational number such that the prime factorization of q is not of the form 2 power n times 5 power m, where n and m are non-negative integers. Then x has a decimal expansion that is non-terminating, repeating. Therefore, for a rational number p over q, if the denominator q is of the form 2 power n times 5 power m, where n and m are non-negative integers, then the rational number p over q has a decimal expansion that terminates. Otherwise, the rational number p over q has a decimal expansion that is non-terminating, repeating. Without actually dividing, Find out after how many places the decimal expansions of the given rational numbers terminate. To find this, we need to express the denominator as a power of 10. In the first problem, let's multiply the numerator and the denominator with 5. Thus, we find that the given rational number terminates after 3 decimal places. Similarly, in the second problem, let's multiply the numerator and the denominator with 2. Therefore, we find that the given rational number terminates after 2 decimal places. In general, we can say that the decimal expansion terminates after as many digits as the exponent of 10 in the denominator, that the highest exponent in the denominator of the given rational number.